Example 7.9 or 8.9 for the given textbooks. For details, please see the description below. Air is compressed from an initial state at 100 kilopascals and 17 Celsius to a final state of 600 kilopascals and 57 Celsius. We need to determine the entropy change of air during the compression process using the property values for air table and the average specific heats. In order to calculate the change of entropy using the values from the air table, we're going to use the following equation. S2 minus S1, the entropy change, is equal to S2 degree minus S1 degree. These values correspond to the temperature-based entropy, or the normalized entropy based on temperature, minus the constant for air and the natural log of the ratios of the pressures, pressure 2 divided by pressure 1. Now we go to the table for the air properties and we evaluate the properties at the different temperatures. For the initial temperature of 17 Celsius, which is equivalent to 290 Kelvin, we find that the normalized entropy is equal to 1.66802 kilojoules kilogram Kelvin. And for the final temperature, which is 57 Celsius, which is equivalent to 330 Kelvin, we find that the normalized entropy is equal to 1.79783 kilojoules kilograms Kelvin. These are the values that we obtained from the table for the normalized entropies, and this is the constant for air. We now substitute into this equation, and we found 1.79783 minus 1.66802. This is kilojoules kilogram Kelvin minus the constant, which is 0.287 kilojoules kilogram Kelvin, natural log of the ratio of the pressures. The final pressure is equal to 600 kilopascal. The initial pressure is 100 kilopascal. Units cancel, and then we find that the final value for this equation is negative 0.3844 kilojoules kilogram Kelvin, and this is basically S2 minus S1, which is the change of entropy in this particular process. For part B, the change of entropy is simply calculated by using the value of Cp average times the natural log of the ratio between the temperatures minus the same component that we have over here, R, natural log of the ratio of the pressures. So now we're going to start with this part. For us to find the value of Cp and average, we need to find the Cp at the different temperatures. We go to the back of the book and we find that the temperature, if the temperature is 290, we find that the value of Cp is equal to 1.0046, and this is going to be kilojoules kilogram Kelvin. And then for a temperature of 330 Kelvin, we find that the value for Cp is equal to 1.0068 kilojoules kilogram Kelvin. So the average value between these two is going to be, so Cp average, we find it to be simply 1.006 kilojoules kilogram Kelvin. Now we take this value and we substitute it over here. S2 minus S1 is equal to 1.006 kilojoules kilogram Kelvin. The natural log between the two temperatures, once again they have to be done in Kelvin, so it's 330 Kelvin divided by 290 Kelvin minus the same component that we had in the previous step, 0.287 kilojoule kilogram Kelvin, natural log of 600 kilopascal, 100 kilopascal. Notice that the units inside of the natural log must cancel. Therefore, the difference between the entropy is equal to negative 0.3842 kilojoule kilogram Kelvin. Notice that using the approximation of the average specific heat produces less than 1% of difference than using the air tables. This is true because the change in temperature between the first and the second state is very small. It's only 40 Kelvin. However, if you have a higher value or higher difference in temperature, this difference is going to increase significantly.